now, and this is when it starts to happen. Yes, we can see a number of our friends and colleagues in the industry joining us now as signing up for this week. What we were talking earlier about before we get onto PAPIs, which we won't start until 10 o'clock, about IR/VR. Tell me, Paul, as a pilot yourself, what does IR/VR mean to you?
Primarily, it's the go, no go for making an approach. And so there are limits below which you don't make the approach. And so it is a very binary figure to start with, especially with very low visibility, depending upon one's rating and one's license. And it's down to the confidence that you're going to be able to make a land, or whether you're going to start briefing for a diversion.
And it's an absolute figure that you know if your plane's capabilities are anything below the figure that is given, that is an absolute no. You go to divert, do you?
Correct, although there's a wrinkle, because of course the plane could be capable, but if the crew are not in check, or one of the two crew is not capable, rated, or whatever, that's even worse, that you have a plane perfectly able to land and the crew not able to. But so there's a combination of things: serviceability of the equipment, capabilities of the aircraft, and then ratings and check for the aircrew.
Right. Well, just for fun, we don't normally take questions in a live webinar, but we are before time, and I want to see how this works. We have Rajendra, who I don't know, but wants to ask a question. So just a moment, Rajendra. Rajendra, can you hear me? Hello, Rajendra, you're muted. We can't hear you. No, we can't hear. Rajendra had a raised hand there, and I presume there was a question to do with the conversation we're having, but unfortunately Rajendra is muted, so we can't hear anything. But I will. So right. So we'll go back to our conversation. So it's basically down to the lowest common denominator then, when it comes to IR/VR, the crew or the plane.
Yeah, and the other thing, of course, is air traffic. Their decisions sometimes in terms of preferential runways. My experience has been where IR/VR has been given in a descending set of numbers for touchdown, midpoint, stop, end. And then as you hold and you wait, you realize that the stop end has improved, and it's sometimes not obvious to air traffic that a swap in the runway direction will unlock some of the backlog. It's amazing how many aircrew I've heard not prompt the question, could we try it from the other end?
But that's one of the reasons, of course, why you have IR/VR measurements both ends of the runway and the midpoint. That does give you a better picture of the whole runway. And of course, the situation you're talking about can happen very much if you're in a, say, an approach over the sea, because you have a sea fog drifting in from one end. And so that end may be in quite thick fog. The other approach may be quite clear, actually. And that's always a nice decision as to, are you going to get to the fog before you landed?
Right. It's now, sorry, just interrupt. It's now 2 minutes before 2 when we will officially start the presentation of the webinar. But for those who are listening at the moment, Paul, Keith, and Tony are describing talking about IR/VR, which will be a subject of a future webinar. Sorry, you were saying, Paul?
I was saying where you get aerodromes that are airports which are close to another airport. I'm thinking of Heathrow and Gatwick. of course, you've got to coordinate changes. You can't just decide to change ends. It's different in some states where there is just one airport that's serving a city. And so even though there may be improvements in the readings at one end of a runway, it isn't the flick of the switch that it might feel like it could be.
There's also a difference in the way in which the RVR operationally has an impact. In a very real sense, your RVR measurement, if you're doing a takeoff, as you taxi out, that's what you'll see throughout your takeoff maneuver. But on the approach, of course, the RVR value you see, how far ahead you can see, the value you're given depends on decision heights, and a whole lot of flying was had to be done to get the relationship so that you could actually control safely precision approaches in lower different visibilities. But it's an approximation to what you see at 200 feet and say 600 meters RVR. You won't see 600 meters of approach lighting most of the time.
And the word slant comes into mind.
That's right. And by the way, at Bedford, we developed a system by sampling up to 100 feet. We were predicting contact height to an accuracy of 3%. Whereas with the RVR, say the RVR is 650, and you expect to see a contact at 200 feet or a bit before. In fact, it can be anything between 180 feet, which of course an overshoot, and 500 feet. And any one day you don't know which. So your actual contact heights for a given RVR can be very variable. We were able to predict very accurately within 3% where the contact height would be. Like we'd say, okay, you've got this RVR, your contact height today is going to be 265 feet. And we did a whole winter of fog flying to show that work. That's what you should really control approaches with your slant range, but it's a complex idea, and I don't think there's the will in the world to implement it.
Right. Well, I think it's certainly something for the future, and certainly something we've discussed. It is now 2 o'clock, the witching hour. So just to those that are online now, I'd just like to, you can see the panel for today's conversation, question and answer session: Tony Smith, Paul Fraser-Benson, and of course, Keith Costall. But before that, we're going to have today's webinar. My name, for those that haven't been on before, is Robert Shapton. I am the Managing Director of TMS Training Solutions. I'd like to welcome you all to today's webinar and remind you that our mission is to provide competency-based training for the next generation of aviation professional. Together with Keith, we're very, very proud to and grateful to Tony Smith, who has accepted our invitation to deliver today's webinar on the subject of the PAPI, which of course he is the inventor, a world-renowned expert on all matters aviation and visual aids. Tony is a fellow of the Royal Aeronautical Society. I have his CV in front of me, and we take up the entire webinar if I describe the absolutely fascinating life and experiences of Keith in aviation. But so I'll just limit myself to awards, which will give you an understanding, an impression of what he's achieved. He's had the UK Government Award to Inventors for the invention of the PAPI, the Precision Path Approach Indicator. He's won the Illuminated Engineering Society Outstanding Achievement Award for the development of the PAPI. The Barnes, in fact, 2 Barnes-Wallis medals. The Guild of Air Pilots and Air Navigators, Sir Barnes-Wallis Medal, 1992. The Royal Aeronautical Society Wakefield Gold Medal, Flight Operations Medal. And Tony has achieved this through being principally a government scientist for a number of years, working principally, I think, at Bedford, Tony.
Yeah.
Where in addition to achieving an tremendous amount of work on a live site in days where health and safety hadn't been invented yet, and you were able to do incredibly exciting yet dangerous things to test the theories and inventions he was working on. But in that process, Tony has authored over 100 technical papers. So I'm personally indebted to you, Tony. You've been a great mentor and inspiration over, in my work. And I'd like to thank you for agreeing to this invitation. And without any further ado, if the panelists could please stop their videos, I will launch the presentation for today on which is the PAPI Masterclass, courtesy of Tony Smith. Tony, off you go then.
Well, thank you, Robert, for that very kind introduction. I say good morning, good afternoon, good evening, depending where you are in the world. Good to be able to talk to you on this webinar this afternoon on the subject of Precision Approach Path Indicator, PAPI. I thought before we went into the details, you might just like to have very quickly a snapshot of where PAPI came from originally. The whole thing started in 1973 when, as Robert said, I was working at the government's aeronautical research establishment, the Royal Aircraft Establishment, and one of my colleagues, leading another section, came to me one day and said, we've just been given a task by our Department of Transport to look into a concept of city centre airports, so that people can actually be delivered, particularly business people, right into the city centre. And this is something we talked about in around 1973. A number of countries, Canada was very interested, putting on a demonstrator. We were asked to look at the whole concept of this. And so we need to do flight trials, and the concept involved a runway 4,000 feet long, 100 feet wide, an aeroplane capable of approach speed of about 100 knots, down a 6-degree approach, coupled to it with non-visual guidance down to a height of 50 feet near the threshold, and then a manual flare and landing. And so I was asked to come up with a suite of visual aids to support that, but in particular a glide slope indicator at 6 degrees, not 3 degrees, because the concept was being coupled to ILS, so you'd have a stable approach. But of course there was no ILS at 6 degrees to do the trials on, and no autopilots capable of flying 6-degree approaches. So it had to be a manually flown approach by the pilot, simulating a coupled approach. So it had to be a very precise approach. So in a matter of a few weeks, with a research program with our test pilots, I came up with this precision approach path indicator, which is what I'm talking about this afternoon. It proved to be ideal for the task, and the cohort of test pilots we had said, this is such an improvement on what we've got currently out there, whether you're talking about military or civil operations. Much more information, particularly at short ranges, than the VARSI, much easier to use. You need to go to the Civil Aviation Authority and to the RAF, and we'll support you and say, please, will you look at adopting this to replace earlier glide slope indicators? It'll be a real operational benefit. That's where it came from. So it was really just a tool to do an experiment originally, but then became a worldwide aid over the succeeding years. So there's very brief background to it. So the precision approach path indicator. What I intend to talk to you about this afternoon is its operational role, its functionality, and the location of it in relation to the runway threshold, and also some guidance on the light unit design, and importantly, the maintenance requirements and the methods of doing that maintenance. So if we move on now to the first of those, let's look at an overview of the PAPI. I want to say right at the beginning, what I'm talking to you about this afternoon is based on what you'll find in international standards. I could talk a lot about how we went through various phases and things we tried, but I'm saying this is the PAPI you will meet in everyday life now. It's in the international standards, all descriptions. and all the key issues I want to talk to you about are related to that. Things that you will have to do in procurement, installation, and operation. And I've got several headings that I've broken the talk down into. The first is the visual cues information that PAPI provides to the pilots. What is it the end user is actually getting out of PAPI? What is it the pilots have and need, and why is it meeting their need? And along with that, the second point is, well, what's the actual signal format and how does it work? How do we convey by visual signals to pilots the information they need? And the third point is, well, where do I put the PAPI? You can see on the diagram before, you can see a typical runway with a PAPI there on the left-hand side, 2 red and 2 white lights. And I'll be explaining that more as we go along. But that's the location of it, and exactly where that is on any particular runway we need to address. And then, of course, well, I've done the research, and I've proved it's practical to do it, and it meets an operational need. But now the biggest job is actually doing the optical and engineering specifications and the manufacture to a unit that in everyday service will provide this requirement. So engineering is a very key part of the PAPI being a successful device. And then the last bullet point, but not the least by any means, the in-service maintenance standards and procedures for this particular part of the aviation ground lighting. So let's look now at the operational role of PAPI guidance. It's a visual aid. I think we all have met here this afternoon. We all know that that's what it is. It has an actual usable visual range in good daytime visibilities out to 10 kilometers in the undershoot. It can be seen quite early on as the pilot prepares to make the final descent towards the runway. And that has its uses, particularly if there isn't any non-visual guidance, that sooner the pilot can settle onto the 3-degree glide path, which is the norm, and stabilize the approach there, get his power settings right, the better his approach will be in all sorts of ways. It'll be safer and it'll be more repetitive as to where he touches down, and that has all operational benefits. So it can be very useful in all very good visibility conditions to stabilize the approach way out. And so that second bullet point, amplifying that, yes, what we're looking for is to establish and maintain a stable approach on the specified glide path angle to an accuracy similar to what you would get if you're flying an instrument approach. That in a sense is the gold standard. That we know from other research over many years. If you do approaches that standard of accuracy performance, you have a very safe system. So PAPI enables you to do that without any non-visual guidance in many cases. The last point there is an important one and tends to be forgotten. We tend to go straight away to, well, what about the PAPI, where is it on the runway? But you need to start any process by saying, what are we using GlideScope information for, apart from just stabilizing the aircraft on a nice 3-degree approach? Well, you're protecting the aircraft from hitting any obstacles in the undershoot, and part of that process does require, in the preparation for PAPI being installed, an obstacle protection surface survey being done to make sure there are no obstacles sticking up into a plane that starts near the threshold and goes up at a fairly shallow angle, but nevertheless an angle that's a degree or so less than the glide slope. And basically, putting it simply, if you stand at the nominal touchdown point and look up this path, are there any obstacles sticking up through it? If there are, you know, if it's a tree, can you chop it down? If it's a chimney, can you blow it up? You've got to have an obstacle protection surface, and then a PAPI sighting such that you've got a good clearance above that in addition for total safety. So you start with making sure that PAPI gives you that adequate clearance over the established obstacle protection surface. So that's so important. And the PAPI also, apart from protecting you against hitting anything on the approach, it can then be quite an important role in some cases in making the maximum landing distance available. If you've got a runway that is fairly short in terms of the operation you want to make with an aeroplane, where the spare distance, if you like, after landing isn't very much, if you're going to have wet conditions, landing distance available can be a crucial part. And if you know you'll land at the nominal point you're supposed to land at with considerable accuracy, much more than with previous aids or no aids at all, that helps the pilot have the best landing distance available. PAPI also, because of its precision, its ability to pick up deviations quickly, protects pilots against the onset of wind shear. And wind shear is something that tends to happen low down, particularly in fairly disturbed weather, where the direction of the wind may shift many tens of degrees to left or right compared to the aeroplane quite suddenly, and the aeroplane will start to descend rather rapidly. And during the trials, which I'll talk about a bit later, we had a number of occasions when pilots said, I got into wind shear below 200 feet. The first thing that told me I was in a wind shear was the PAPI talking to me. So it meets that requirement for the latter stages of the approach. So let's move on now to the actual signal format. What is it the pilots actually look at? What do they actually see? Well, the signal format, as you can see from the diagram on the right-hand side of the screen, the PAPI is normally on the left-hand side of the runway, upwind of the threshold by a distance that will ensure adequate clearance over the threshold, and we'll talk a bit more about that later. But they're high-intensity lights in that bar, a horizontal array beside the runway. And each of those 4 units is effectively something that projects a beam of light. The top half of the beam is white, the bottom half of it is red, and the transition from one color to another actually occurs over a very, very small angle, very, very small. And that color change and the accompanying intensity change, which are all part of the signal, that appears when you're actually flying and operational use to be instantaneous to all intents. It flashes, it clicks, it's attention getting. And the final thing about the signal format is those 4 units to produce the array you see on the right, the various positions, 4 reds, 3 reds, 2 reds, 2 whites, which is on slope, and then 3 whites and then 4 whites as you go high. That sequence is achieved by setting that transition angle at different angles above and below the glide slope, progressively higher angles from the outermost light, so that the glide slope is actually sitting between the middle 2 lights. So when you're on the glide slope, you should be seeing 2 white and 2 red lights. That's the signal that pilots look for and try and achieve, is 2 reds and 2 whites. So let's look at the setting angles a little bit more now. Here again, as a diagram available in all sorts of things, including the ICAO and X14, that shows you for a PAPI and in fact for an APAPI, and in some cases an APAPI will be adequate, particularly for smaller aircraft, general aviation. An APAPI will provide an adequate guidance where you just have a red and a white. So you have 3 signals then, two reds, 1 red, 1 white, and 2 whites. That can be very useful in quite a lot of settings. So you've got those 4 setting angles. They're 20 minutes of arc apart, a third of a degree apart in the normal PAPI configuration, so that from top to bottom you've got a total coverage of 1 degree, and those angles designate the place where you get a change of state from from the number of each coloured lights. And so this, I call this a digital signal format. It's very, very evident which it is. There are 5 states, and only 5 states. And this is from background knowledge. This is human factors says for a glide slope indicator, 5 bits of information is the ideal, certainly for larger aircraft. You don't need any more. You really don't optimally, in many cases, need any less. 4 is ideal, and that is what PAPI provides. 5 discrete stages, which are very obvious which state you're in. And it achieves in practice, as we found during our trials and found out in practice over years, it provides a very stable, accurate approach. And but doing this, because the aid talks to you, if I use that phrase, because if anything changes, it's apparent. You may not be looking directly at it. You may be looking elsewhere on the runway, or even quick glances into the cockpit. The pilot has got a lot of things to monitor. And if something suddenly changes its state outside your central field of view, which is only 2 degrees wide, you can't look at 2 things identically. If you think you can, go to a book, look at the spine, concentrate on that. You can't read any of the text. You have to move your eye view. So, but it's in the periphery where things changing, either state or movement or something, that distracts you. And this is what PAPI does. So the pilots can trust it, that if anything is changing, it'll shout at them, as it were. So that's where setting angles are so important. Let's move on now to this 3rd area, which is the choice of location. This is a very important factor. Where do I put this device in relation to the threshold? Normally we refer to distance upwind of the threshold. We've got to bear in mind, as I said, where the obstacle protection surface is, that where we're going to put it will give us that clearance above that surface to get the element of safety on the approach that we've needed. And then secondly, as we come to the runway, that the wheel clearance at the threshold must be a certain value. This takes a care of the fact that even with the best aid in the world, a pilot flying a PAPI, there are small variations from the glide path. It's also true with the ILS. And the ILS, the autopilot, they're not absolutely perfect. They won't drill absolutely lines in space. Day to day and place to place, there are variations. And that sort of area of uncertainty is taken out of the equation by saying, well, in the datum case, we'll have a wheel clearance of a certain amount, and you'll find this in Annex 14. The smallest that's shown there, the smaller aircraft is 6 meters wheel clearance at the threshold, but other aircraft as much as 9 meters. So that has to be built into the decision as to where to put the PAPI. And the 3rd thing is, at many runways, and this is desirable for a number of ways you do this, even if you've got an ILS, you put a PAPI in, so that aircraft using that runway that haven't got ILS have still got glide slope information. It may be that the ILS is unserviceable. That does happen. It's very reliable, but it can happen. And there have been a number of accidents at places where there was an ILS, but no PAPI, and then the ILS went unserviceable. There have been accidents, I remember 1 or 2 out in the Pacific region, where pilots on the approach flew into a hill. They got too low. They were coming down the side of a hill. They got too low on the approach and hit the side of the hill. If there'd been a PAPI there, they'd have been aware that they were too low. So that wheel clearance and that harmonization, all those things are all part of the package. And so harmonizing signals. So if you have got both of them in use, the pilot gets an on-slope signal if he's stabilized on the glide slope, whether it's he's looking at the PAPI or whether he's relying totally on the ILS. he'll get the same indication down to the point where it stops being of any particular relevance anyway as you approach the threshold. By the way, this is an approach path indicator. It's not a landing aid, it's an approach aid. And the ILS stops using, the ILS approach stops using the ILS signal just before you get to the threshold anyway. It uses radio altimeter. So harmonization down to those low heights is important. And the choice of where to put it, there are other influences, if you like, second order effects are very important. You've got the actual runway layout to take into account, the airport layout of taxiways. You may have a crossing runway fairly near the threshold of the runway you're putting a PAPI on, which means that where you come to put the PAPI will actually be in the middle of another runway. Or more likely, you've got a taxiway which comes in to the runway just at the point where you want to put your PAPI. And so you may have to make some sort of compromise as to where you put the PAPI. One way of overcoming those sort of difficulties is maybe you'll put it on the right-hand side of the runway rather than the left-hand side, which is the conventional normal use on the basis that the captain of the aircraft, the person in command, is usually in the left-hand seat. So give them the best visual aid, as it were. But frankly, either side produces exactly the same result. And either side will do, but most are on the left-hand side. And then, of course, you've got topography, the variations there may be in runway, there may be runway slopes, there may be crossfalls, there may be fairly uneven ground off the side of the runway. You have to make allowance for those, and there's guidance in the various manuals of how to achieve that. And the best way of doing a choice of location is, in my view, that you get competent people who know from various professional areas, want to put their input in, and together you make the decision under what I would call an aeronautical study, using the ICAO standards as the basis. And for your particular case, come up with the best choice of location. And I'll say a bit more about that in the next slide. So what are some of these operational issues? Well, I keep saying, and it's important to say so, this is a presentation based on showing you what the ICAO standards are. However, having invented this device, I have to say that when I look around now, I look at the words which have been massaged a bit over the years. If you look at Annex 14, basically we've got a specification that is 40 years old for the location. Not the PAPI itself as a device doesn't need any change, but some of these issues need addressing because operational circumstances have changed and will go on changing. And I believe, to say to the aviation committee, it's about time that those parts of the standards were reassessed. And I believe to the benefit of everybody, our safety would, if anything, be enhanced, application would be easier and more in keeping with the sort of aviation we're seeing now and we'll see in the next 20 or 30 years. And the harmonization method that assures this wants to make sure that we take account of the actual performance of aircraft. The whole thing about PAPI installation, fairly shortly after it was adopted, the 747 became the dominating concern of everybody. And that makes a location which is suboptimal in many ways in the harmonization process, which we could go into a little bit more. But and there are ways around that achieve a suitable answer. But it gives you an additional problem. And what I hear and understand and see over the years, the 747 will go out of service. The airlines are using them, going to use them before coronavirus, less and less. But they'll still be in use, certainly carrying cargo for quite a long time. but the frequency with which you're going to get 747s into a runway might influence where you decide to put your PAPI. The other thing that occurs to me is that we're talking about harmonization with non-visual guidance, and we talk about ILS. What's coming along, of course, is GPS approaches. There's no aerial in a GPS approach. I suspect that what will happen is that approaches will have to be regulated simply by threshold wheel clearance. That'll be the basis on which the predication of where the GPS glide slope is calculated to be. So watch this space. There may be changes related to the form of non-visual guidance that needs to be taken into account where the location of PAPI is to be. So if we move on now, having looked at some of those operational issues, let's look operationally at how this PAPI functions. Well, PAPI, first of all, was designed to meet the 4 criteria that any good visual aid has for visual signaling. It's a visual signaling exercise, and for any visual signal, you need a signal that's conspicuous, which is legible, which is comprehensible and credible. And by that, putting it another way, conspicuous, it should be, when you want to start using it, one glance in the general direction of where you expect it to be, it should stand out and say, here I am, I'm ready for you to use it. It should be conspicuous in the background. And of course, in a busy urban environment, a busy environment with an airport with an awful lot of lighting on, it's important that the PAPI can be quickly located and be conspicuous to the pilot. And then the signal's legible. It's all very well if we've got a row of lights there, but if the pilot can't discriminate between the 4, and he just gets a sort of blurred bar of lights and can't get any real information out of it, it's not legible. If you can't read the signal, it's not doing its job. So it needs to be legible. It needs to be comprehensible. In other words, when the pilot sees these lights and sees them change, he understands what's happening, or she understands what's happening, and he or she says, oh, I'm not only can I see what's happening in the PAPI, but I believe it's telling me the right thing, it's credible. This whole business actually, just go back to the comprehensible. One of the features of PAPI is it's so easy to learn and understand. During the trials we did before the implementation in the UK, we put PAPI on the left-hand side of a runway at Gatwick and the runway at London Heathrow for 3 years with the VASI on the other side for comfort's sake, for pilots who've been used to that. And for 3 years, we got pilots to comment on the PAPI and its usefulness and so on. That was run by CAA. They analysed all the data. And we had the story of one pilot, a long-haul pilot, who'd been flying segments, to the other side of the world and gradually coming back to the UK, been out of the country for perhaps a week or more, coming back, hadn't seen the notice to airmen saying that PAPI was going to be switched on at the beginning of that week, and this is what it did and so on. So he got no information. He went to his company offices to do his paperwork, having arrived back at the airport, and said to the staff in there, I don't know what it is, but somebody's put a row of lights beside the runway, red and white lights near the touchdown point. And they snap over, they change colour, and they're red and white. And if you maneuver the aeroplane to get 2 red and 2 white lights, lo and behold, you've got a 3-degree glide path. So that said to us very firmly, well, I think we've cracked this one. It's fairly easy to interpret and understand. And that little story, I think, illustrates the point. The other point is the task difficulty is low. I've already mentioned this. It's very important that pilots are busy at this stage. It's one of the busiest stages of the whole flight, is the final approach and landing. and then the taxi in, and there's a lot of things to be taken care of. And so having to stare at one particular aid to the absence of any other good time to look at anything else is not what the pilot wants. He wants a low task difficulty device, so he can have spare capacity for other things. And PAPI's been shown to have that the task workload is low. And then for this PAPI to operate functionally, safely, I just emphasize some of the things I've already said in one way, but say them again because it's important. What we have is the PAPIs to be operated safely. It must have a performance that meets the specifications that you can find in Annex 14. First of all, that high intensity beam has to be compliant with the beam spread you'll find in Annex 14. Enough vertical and horizontal beam spread to enable the pilot to get information above, on, below the glide path, to left and to right. He doesn't have to be absolutely lined up with the runway when he initially sees the PAPI, but if he can, on a visual circuit, particularly a fairly tight circuit, we did during one trials period, we were at an airfield where a lot of training was being done, and the chief flying instructor, when we said, well, that's it, we've done our trial, thank you very much, said, please will you leave the PAPI here, because when my pilots are flying base leg, I can look and they can look very early on, before they're anywhere near lined up. They can see if their height is correct, if they're on the right glide path. They can nail the glide path information very early on in the approach. So it's a very useful training aid, that azimuth coverage in the beam spread. The color transition, that's important, of course, I've already stated. It is so important that color transition, you really don't see any other colors other than red and white. It does go through a transition in that very small sliver of 1 or 2 minutes of arc, but in operational use, you can't see them. There's no other color you have to look for or expect to see. You see red or you see white, and both the color and the intensity are part of that thing where it clicks over. And I would just say the original PAPIs had a 5-to-1 intensity difference between the red and the white. That enhances the signal. If you had equal red and white, PAPI would still work, but you're taking away part of the functionality, the sharpness of the transition, the eye-catchingness of it. So whilst now, somebody in the laboratory might think, oh, with new light sources, I can match the intensities. Wouldn't that be a good idea? No, it wouldn't. Don't give in to the blandishments of any manufacturer who tells you he's got a wonderful device where the red and the white are equal intensity. He's actually detracting from optimum performance. The signal colors need to comply with the international standards to get this sharp transition. If you have so-called reds, which are really quite orange, you won't get this sharp transition. So the equipment manufactured and measured in the laboratory, the colors red and white must be coincident with those standards that you find in Annex 14. And the setting angles, which are the angles of where the transition is, they must be in the unit, they must be correct and stable. The whole usefulness of PAPI relies on those 4 setting angles. And so when it's in use, those angles must be displayed correctly and in a stable manner. So let's look at the thing that influences that, and that's the optical and engineering design of the unit. There are 4 elements to this specification. From the lighting point of view, particularly, first of all, the isocandela diagram. The design must provide that specification. shown by the ISO candles in the diagrams you'll find in Annex 14. Secondly, the colours that are provided with the filter material or the light source, or the combination of them. They must be signal colour white, signal colour red, and the more saturated the way the red can be, the more near it is a perfectly saturated red, the better for recognition point of view. And then another thing in the actual optical design is to produce and maintain this sharp signal transition. That's very, very important in the design, that you have built in that very sharp transition. And finally, from the optical point of view, that you then are able to have some device you put, you measure where the unit is pointing for the setting angle, that angle that you then set by whatever means you do it is indeed the setting angle you require. It is the transition signal angle as well. They need to be harmonized at all times in the optical design. And then from a more engineering point of view, that leads on to the fact that you need positional stability of the projector components. Typically, you've got a light source, you've got a holder in which there's a filter. Certainly in the original design, you have a red filter there covering half the aperture, and then you've got a projection lens at the front. Those three elements need to be held rigidly in place in relationship one to another. And we found the best way of doing that was to have a base plate, if you like, onto which those three elements are very firmly attached and fixed, so that you've got a base with three elements which are all in permanent equal position relative to one another. Very stable. You're buying a precision projector. That's what you should be buying when you look to purchase it. Just as a theodolite, you don't want a theodolite where the parts inside move about. You know, anybody doing a survey would not buy a device where the components that he's relying on to make the measurement could move about. They need to be very firmly held in place at all time. You need, in the engineering, to make available means of doing adjustments, leveling the unit and putting the appropriate setting angle onto each of the four units. And finally, the design must take account of the environment that it's going to be operating in. Out there on the airfield, there will be jet blast, particularly if you've got a runway where aircraft enter the runway and then have to do a turn to line up. They may well be giving you a good piece of jet blast onto your device. There's the issue of condensation and ice, environmental issues there. Condensation and ice, we did a lot of tests and showed that you can, as long as you keep the inside of the box temperature sufficient, so that no condensation can happen. You keep the glassware of the lens, in fact, above the ambient temperature. The outside world, you won't get condensation, and also conditions where you get ice that can form. We went through winters, we went to quite low extremes. Provided you've got some heat there, which you can provide either by underrunning it, certainly on tungsten halogen, you underrun so there's no light comes out of the PAPI, but you leave some small current so that the infrared keeps inside the box warm, or you put a small wattage heater in the box. There are standard ways of doing that, and of course then you've got to take account that you will have lamp failures, and you need to have a design such that you can change lamps without having to dismantle the box. These easy lamp change is important. So going on now to look again a little bit more at engineering design principles. Just to go back to very basics, what we're talking about here with the PAPI is a slide projector. And I guess almost everybody watching today will have had a slide projector if they still haven't got one. The days when you took 35mm pictures with your camera and then did a slide projection for all your family and friends, projecting it onto a wall or a screen, focusing it on the wall. It's a nice sharp picture. Well, that's basically what PAPI is. It's a light projector, but on the wall you will get an area of light. The top half would be white, the bottom half would be red, and there would be no fuzzy area in between. You should focus it so it's a sharp line between the white and the red. For the PAPI, we don't focus it on the wall in our room, we focus it at infinity. And that's the way in which we get a sharp transition at all operationally useful ranges. As I already said, make sure the optical components are rigidly related one to another, and that you've got leveling plates and setting angle plates that really do tell you the right information. You know where the beam actually is that's coming out of your PAPI. You must be able to align this box, align the signal coming out of this box. And so my last point is, I shudder when I see people saying they put an inclinometer on the lid of the box to set the setting angle. And when I look at this box, it's a fairly thin ply, fairly thin metal, providing prevention and ingress of sand and snow and so on. But the whole thing isn't rigid, and that is just not on if you're going to produce a proper PAPI signal. You must have a rigid box structure, and so except for exceptional curves, I mean, somebody is going to run into it with a maintenance vehicle, or an aircraft is going to land on top of it. They may displace some of the optical components, but basically it should be pretty immune to any misalignment like that. So having said we've researched, we've developed, we've installed, we've got an aid which does the job, how are we going to ensure that it continues now we've got it in place, that it does continue for the long term to provide what it's there to provide? And this is where maintenance comes in. And I'm so glad that I'm able to say a lot more about PAPI maintenance now than I could do a few years ago, because it has been very much a neglected area, is adequate maintenance. But as we'll hear, work has been going on now to actually provide proper tools, because maintenance is actually essential if you're going to have safe and efficient, effective operation of PAPIs. There has to be maintenance, and people who've owned PAPI have been struggling, a bit mystified about, well, how do I know if I'm providing the signal that I should have? Good maintenance means of knowing that you've got what you should have and can verify that. That's important, and that's what's coming and is available now. Good preventive maintenance procedures, so that the aid is available at all times when it's needed, day in, day out, night and day. And I want to say, for some of you listening perhaps to this who've got a PAPI and not quite sure how to maintain it, and perhaps a little hesitant about touching it because it's a precision instrument, it's actually quite robust and will stand up for itself, provided that you have got the right diagnostic tools to check its performance, that you've got the procedures to use that equipment, and that you've had the training to use it. So the key is having a device where you can sample what's coming out of the PAPI, and know how to use that device, have the adequate training, so that your use of that device will sort of guarantee that PAPI is indeed properly serviceable. And of course, this equipment, I've already hinted at, is now available. I know at least one that will make the in-service, in-field measurements for you. It will measure intensity, it will measure colour, and the setting angle of each of the 4 units. And the benefit of this is that you can now have a very straightforward maintenance procedure. You can determine how frequently you need to do the measurements. That will vary perhaps from site to site. You'll know that you can do this, and what's more, if you have this aid, and here you see a picture of the aid that's been fully developed and evaluated, you'll get records. In this day and age, you'll get records of that intensity, the signal colours, and the setting angle, and where the transition angle is. Of course, they should be in the same place. The setting angle should be at the transition angle. All that can be checked for you, be downloaded. You have that information, and at first level, you can very rapidly know, well, is my PAPI serviceable or not? You can have a sort of pass-fail at the first level. But then you can go, if there is failure or partial failure, and PAPI does fail soft in that if you've got a 3-lamp device, if one lamp goes out, the PAPI is still usable, but does require maintenance as soon as you possibly can and replace the failed lamp. But you can see what's failing. You can see if there's a repetitive failure. Maybe it is due to movement of the base. Maybe your bases aren't as stable as they should be. You'll begin to get more information about that particular site and that particular PAPI. So you can then do deeper diagnostics offline, as it were. And finally, and importantly, you'll have a record of what you've done, so that anyone who wishes to inspect the quality of your maintenance, you can show them your compliance records. Well, there we are. We started 40 years ago. We've come up to really the present with a fairly new device that I think is going to enhance the usefulness and the way in which you can use and maintain PAPI. It's going to take it a step further. So I think at this point, good place to stop talking and to move over to a phase of question and answer, I think, Robert.
Thank you, Tony. That was absolutely wonderful. So there you have it from Tony, inventor of the PAPI, how it happened, why it happened, how it works, and how to make sure it carries on working in life. So I see we have a number of questions coming in. If I could ask my fellow panelists, Paul Fraser-Bennison, Director of Merlin Aerospace Consulting, former member of the Visual Aids, ICAO Visual Aids Committee, and leading visual aids expert at the Civil Aviation Authority in the UK, and known to many of you. Keith Costall, who I think you all know, Director of TMS Training Solutions, and an expert in all things visual aids. I think you'll all agree that that has been Paul, if you could unmute, I think you'll all agree that that's been an excellent presentation, highly informative, and we've had a number of questions from our delegates here. So so we have 10 minutes officially, but we'll run over a little bit because there have been a number of questions. First questions: how can harmonization of the PAPI be achieved with ILS, and what are the considerations we need to account for during PAPI sighting? Now, Tony's talked about it a bit, but I know, Paul, you have some input on this.
Yeah, shall I just say, I think in a way I've dealt with that in what I said. I said if you go to guidance, which I think Paul probably wrote when it was in the CAA, it will all become very, very simple where you locate the PAPI. I think Paul needs to talk a bit about this.
Well, yes, I think the situation in the UK, and I can only ever speak for my experiences at UK Aerodromes, is that ILS was installed before PAPIs to a great extent. There have been more ILS installations since. But I think the harmonization is always going to be the visual aid to the existing instrument landing system. And so the guidance that was placed in CAP 168, which we're going to hopefully put into print for people answering questions, gave some advice as to how to harmonize for the different sizes of aircraft. And of course, if you look in the guidance, there is a difference in the angles between 20 and 30 minutes of arc when one has to harmonize to an ILS as opposed to a normal glide path.
Thank you.
Could I just say that what Paul's saying is what the practical solution that's in Annex 14, if you've got a wide range of aircraft types with large different wheel heights variations, if you're just putting a PAPI in, and we're going off harmonization now, but the basic PAPI is 3 equal 20-minute increments. So if you're asked to put a PAPI in and there's no ILS, it's 20-minute increments you should go for. They're the optimum for a 3-degree glide path.
Right. And there is we had a lot of discussion between us before this presentation and prior to that indeed. And there are some difficulties and issues with the wording in Annex 14. And so we've all agreed that in fact, CAP 168, published by the UK CAA, Appendix 6B, sighting and setting angles of PAPI, is probably the simplest and clearest description of, and so for those of you who are interested, we have 2 papers we'll post on our TMS Training Solutions webinar website. One is the Appendix 6B from CAP 168, which will briefly in 6 pages describe where to place your PAPIs relative to the ILS according to your local conditions. And secondly, also a paper published by Tony and Chris, a colleague of his, sadly departed, Chris Hedge, who are on the topic and the issues surrounding sighting of PAPI. So those will both be appearing on our website after this presentation. Back to the questions.
Question, could I just interact here? Another element internationally is that we've been speaking about the different angles, where we talk in angles in degrees and minutes. In some places of the world, they use decimalization. So instead of it being 2 degrees, so many minutes, they may talk about 2.8. And that's something to be very careful about.
Thank you, Keith. That is a very good point. And it needs to be very clear because the differences are quite significant. You need to be clear if you're talking in decimals or actual degrees, minutes and seconds, of course. So carrying on with the questions from our participants, Khaled El Orf has asked, if a runway there's no AGL, PAPI is mandatory, even if the runway is only intended to be used at daytime. So do you need to have a PAPI? Under what conditions is a PAPI mandatory? Paul?
Well, certainly there's nothing in my booklet that says anything about it being a requirement. Clearly it's an enhancement. At night, that's a different matter. So I would say the simple answer is that there is no mandatory requirement for day use of a visual runway for a PAPI. It is supplemental though.
Can I say something about that as well? Hello?
Yes, of course, Tony.
Yeah, I actually got involved in an accident investigation quite a few years ago. A company aircraft, 6-8-seater aircraft, flying around the UK in not very good weather, rain and so on, in sort of November when the weather wasn't good, making an approach to a small company airfield where the final approach was over water, and he landed on the bank of the river, landed short, and killed everybody on board. The visual aids were virtually non-existent, and there's certainly no glide slope information. If you'd have had a glide slope indicator, I'm convinced that the aircraft would not have got into that parlous situation. And other situations I've seen where pilots, you know, they've gone into a fairly rudimentary situation where they've got to start operating. They've said to me time and time again, the first thing you put in is a glide slope indicator, because that's the most difficult axis to stabilize. And if I've nailed my glide slope, I can then worry about azimuth alignment.
Right, thank you, Tony. Next question from Mark Timms. Keith, you might want to answer this one. Typically, PAPI is sited just on the left side of the approach direction. However, many UK military bases adopt PAPI installations on both sides of the approach direction. What are the deciding factors and pros and cons of each installation type? Keith.
Well, from a practical viewpoint, is that you have to look at as Tony has explained. You know, it's the function of the PAPI. You know, and the function of the PAPI unit is to enhance and enable a pilot to be able to safely approach at the designated glide slope and touch down safely. Now, there's two elements that I always consider, is that while the standards, they're very, very clear, preferred it to be on the left-hand side, but you can, if they're for aerodrome layouts, etc., as Tony said, put it on the right-hand side or both sides. If you have it on both sides, there is the added feature of that should one PAPI fail, I mean, it is questionable and have different views around the world whether a PAPI electrically should have two supplies to a PAPI wing bar. That is, should it be interleaved? But if you have two PAPIs, then if you have one on the left-hand side and one on the right-hand side, then should one PAPI system fail for whatever reason, then you have always got the other PAPI and you have still got a 100% compliant operation. So that's one element. But if you also have PAPIs on both sides, it provides roll guidance to pilots. So that's an additional aid to pilots. And so I think that's my answer to that one.
Thank you, Keith. A number of questions to get through. We'll do our best to cover them, but there are an awful lot. To the extent we will not get through all questions today, but we will answer them all and post answers on the website. But again, if anybody needs to contact any of the panelists individually or like to contact us collectively, please, you can reach us through our website. Next one. Hi, this is from Dean Williamson in the Caribbean there. So, hi Tony, what is your opinion on the use of UAVs in the calibration of visual aids such as PAPI? Can UAV provide an equivalent data set for calibration as would be attained by a flight test by a manned aircraft?
Well, there's one thing I'd like to say, and that is, as the last UK CAA flight calibrator, I was checker for a number of years, and when I left the CAA stopped doing flight calibration with manned aircraft. I'm obviously in the original old school camp, and so I would tend to suggest that there's a lot you can do with manned aircraft because of the ability to get to both ends of the runway quickly, and also to get out to the acquisition points, which can be 6 to 9 kilometers away. But that said, UAV technology is improving, and I think close in, say from about 200 feet, there could be reasons why the level of data that you could gather from that would be better. Robert, you and I worked on UAVs some years ago, and we recognized that battery autonomy, access for land, and also for pixelation within the capabilities of the cameras at the time were an obstacle. And of course, in the UK, we had the situation at Gatwick where a rogue drone closed Gatwick Airport for a number of days. And so there are still, I think, a bit of jury out on it. but I think capabilities are increasing on UAVs and costs are reducing, whereas costs on aircraft are increasing. So it could well be that they eventually do replace manned flight calibration aircraft.
I've just add on, if I can just add on that point, that our experience was that commercial insurance for testing PAPI or other visual aids for that matter on commercial airfields was we've been unable to get it on first hand, but relating to PAPIs specifically, we were able to allow to do testing, but for commercial purposes, we were unable to get insurance to operate it as a business. In relation to other measures, though, you cannot reliably, you can get setting angle from a drone, but you won't, I think measurement of the transition, the range of the transition would be extremely difficult. The precise measurement of transition, which is a key criteria in getting the click Tony speaks of. Also measuring the photometric performance of the red and white, you don't get from a drone, and also the color measurement, photometry color measurement. But that was where we got to on that. But it's certainly in the back drawer for consideration. Tony, you had a point.
Only that the original attempt, what was done, and Paul was part of this, the flight test, flying horizontal, well, looking at the functionality, maneuvering up and down and seeing that the colours changed in the right order, and then flying level at a certain height and timing the interval between. If you look at the accuracy of that you can do that, it doesn't compare with other methods and the sort of methods you're proposing in terms of accuracy. It's very difficult to get a really accurate calibration of where the actual angles are. You can look at the functionality, yes, make sure that when you're low, all the lights are red and then they go in the right order. And roughly, if you're flying level, the intervals between the clicks are approximately equal to show that there's, but it's a wet finger in the air, sort of quick look. So there's nothing major, but it isn't a proper calibration in my mind.
Thank you. I've got a question here from Andrew Badham. Good afternoon, Andrew. Andrew from the UKCA and current member of the ICAO Visual Aids Working Group. In fact, leader, I believe. So, and Andrew's asking if, Tony, would you consider putting up a paper to the ICAO Visual Aids Working Group of the Aerodrome Design and Operations Panel on updating the criteria for inclusion in Annex 14? There you are, put you on the spot.
Well, yes, I thought I'd finished with the Visual Aids panel nearly 20 years ago. But no, I think actually this is an important topic. And I think, yes, I'd be up for doing something for a CAA submit. I would like to take my fellow panel members with me. We could develop something online, but I think it needs more than me to get a document that would properly meet where we're going in the future. With slightly different inputs, slightly different views. It needs to be a really powerful document, and I'd very happily start to draft something, but assuming one or two other people would come on board with me.
Right. Okay. Well, the challenge has been put down and accepted, I think. So we'll take that further with you directly. Next question we have here is from Andrew as well, asking, a number of aerodromes are fitting LED PAPIs. Are there any operational considerations we should be concerned with? Anyone in the panel like to take that one?
Well, I think one of the points to just pick up on that, of course, is the decrease in availability and increasing cost in tungsten halogen lamps, which the industry is seeing across all sorts of fittings. PAPIs are not exempt from that because of their light output being required for tungsten halogen. And so I think the first thing to say is that LED PAPIs will eventually overtake tungsten halogen PAPIs. But the whole thing about them is that they are not fit and forget. And so it's important that planned maintenance for all the peripheral aspects of a PAPI, whether it's a light engine from LED or from a tungsten halogen lamp or from any candles with a reflector, it doesn't matter what's producing the light. All the normal requirements for planned maintenance and inspection remain in place.
Thank you. Any more? Certainly, this is it's early days, and I'm sure that I'm sure LEDs will have their place with PAPI lights, as with all other airfield lighting as we go forward in the coming years. I have a question, next one from Wayne Rolfe, who we know very well. Hello, Wayne. Wayne says, hi, Tony. Glad to see you looking well. Always great to hear your thoughts on the history of PAPI. What are your thoughts on the following? 1, LED PAPI and the use of digital inclinometers. Would you agree airports should also check PAPIs manually, the old way, to verify the digital inclinometer is accurate by internal alignment plate or theodolite? Tony.
I would say our experience in developing PAPI, I mean, from the point of view of actually having the first one built by a model maker, if you like, as I stressed in my report, my presentation, the design, so that effectively you've got a precision optical instrument with the components held rigidly and firmly in the correct place is important. And what we then, in our equipment, we then attached an alignment plate to the base plate, so that we use a clinometer to do all our setting up. And all I can offer and say is, over the 10 years in which we were at various stages doing trials, that always gave us the correct answer for the setting angles. And to my mind, that was a perfectly satisfactory way of setting up your angles. And because in a sense, if you've got the lamp, the filter and the light on a particular base, and your alignment device can be attached to that, that's better than some other method, which may be one step removed from that. It may be quite sophisticated sensor, but you are introducing another failure path into the process. And I was always quite happy with the basic, but in practice, very accurate and repeatable means of setting the device up.
We have, I would note that having tested a number of PAPIs recently, that I've personally seen that instances where, and this is something for all airports to be careful, where the maintenance is done in the workshop, the PAPI needs to be transported very carefully. Projector that needs to be transported very carefully to the PAPI site, because what's happened is the internal mechanism, the filters have come out of alignment in transportation.
Indeed.
That's such that the clinometer gives a good reading, but the PAPI, the transition is setting angle is not, and transition are not where they should be. So.
I think
another aspect which it should be taken into account during the maintenance is that when maintenance personnel, whether that it's as a preventive maintenance process or breakdown, and they're checking the angles in an operational PAPI, then if they find those angles to be out of tolerance, the engineer on the ground does not make that decision to change the angle, to adjust it, because they have to report it through to operations, because a PAPI system will, in most places, need a flight check before it is operationally serviceable. So the engineer on the ground, the technician on the ground doesn't make that decision, right?
No, I agree. Fundamentally, what we worked on the premise that we've designed, built, and procured a precision instrument, basically that we rely on that it will produce the required signal. But know that yes, indeed, inappropriate treatment, either in transit or some vehicle hitting it, the internal optics can be severely deranged. But one thing I'd say is we did have occasions where if you've got a 3-lamp projector, and this is where multiple lamps are important, you often see one of the 3 close range. You can see this eyelid of color change. You can see which of the 3 lamps, which lampway has been knocked out of shape. There's a lot of diagnostics you can do like that, actually. But we only ever had a really serious malfunction on one occasion when we sent the equipment halfway around the world for somebody else to install, and never mind 3 degrees and 3 degrees 20. The people who installed it saw 3 degrees, 3 and a little naught, you know, for the degrees, set it up at 30 degrees. And so when my lab technician went to inspect it before installation, he found these things pointing straight at the sun, and all the filter glasses had cracked because he'd got a tropical sun focused on a piece of red glass, and it cracked. So you know, you can there's a limit to what you can protect against, and I think some of those things are misalignment. People after they've been in the maintenance place back out to the airfield. I think that's dealt with procedurally and with training very largely. You know, you've got to train your people to handle this thing with care. You know, put it in a box, say, handle with care as you carry it around. Don't just toss it into the back of your servicing vehicle.
Right. Thank you, Tony. There are an awful lot of questions here, and we will answer them all on our website. But I'll just leave one last question for Paul Collins. Typically, we look to install the 4 PAPI wing bar units at the same optical level, in brackets horizontal plane. However, there's also a requirement to ensure the units are mounted as low as possible. That is, allow for any transverse slope with a lateral gradient of not greater than 1.25%. What would the panel recommend as being the overriding criteria? A level horizontal plane or mounted as low as possible?
Maybe I could comment in on that one. Certainly, you know, having installed and commissioned many PAPI units, clearly it's a horizontal bar. Eh? At the end of the day, we're looking at the 4 PAPI as a PAPI wing bar. We're looking at 4 PAPI units, and ideally, we like to see them in a straight wing bar. Now, if they're a sloping ground, then clearly that if it exceeds a particular slope level, then you would not see it as a horizontal, look like a horizontal bar. It would be obviously at an angle. Now, if that were to be the case, then there are places where we actually stagger the PAPIs so that to the pilot coming in at the glide slope angle, the pilot still sees it as a horizontal bar, and that's. But yes, there is the criterion 1 in 25 in some of the manufacturer's guidance for the slope. So up to 1 in 25, yes, that's acceptable. But beyond 1 in 25, then you stagger them for installation.
I think this is where good knowledge, operational knowledge in the location discussions is important. Because what I would want to say is the innermost PAPI box is normally located 50 feet from the edge of the runway. That's the so-called runway strip, and that's about perhaps an underwing engine way outboard and the aircraft coming up the side of the runway rather than in the middle. It gives you that clearance there, that 50 foot. There shouldn't be anything above ground level there. By the time you get out, perhaps the worst case, the outermost light, you're a long way from the runway. And frankly, if you're going to hit that with an aeroplane, I suspect the aircraft has got other problems on its hands other than worrying about the fact it's going to hit a PAPI box.
Right. Okay. Thank you, Tony. One question here specifically for. I'll do one more specifically for Paul. What is an This is from Hugh Radaby. What is an acceptable tolerance when calibrating PAPI and APAPI lights? This question refers to both instrument and non-instrument runways.
Well, I'm wondering what the meaning of the word tolerance is. Is that in terms of angular displacement or in terms of lateral? I'm not quite sure of the question. I'm just looking for it actually on the on screen. Let me come back to it.
It's question 2, Paul. If you, well, we'll answer that one. We'll answer that one on the website. We're now 20 minutes past the hour. So thank you very much, panelists, for that, for those answers, and of course Tony for a magnificent presentation. It's been very informative. We've never had so many questions, so we've got a lot of work to do when this webinar is over. But we will answer all your questions. If we need any clarification on any points, we'll get back to you. Thank you. And if you've got any more questions for that matter, we're trying to do something useful here. We want to help you, so please ask them, send them in, and we will respond to you personally or to the group as a whole, as you wish. So thank you very much, panelists. Thank you. Very special thanks to Tony, and thank you everybody for participating this week. A copy of the webinar will be posted as well. Next week, we're doing a webinar on airfield lighting, serviceability and compliance, and the reasons for non-compliance. So we'll be covering some specific airport examples and to give you some ideas as to how to maintain your airfield lighting better, so or serviceably. So thank you very much, and I look forward to seeing you all next week. Good night.